Hello, I'm Roman, and welcome back to the series of videos Neural Networks from Scratch, where we dive into what a neural network is and implementing every single thing, well, from scratch. And to do this, I'm using this book called Neural Networks from Scratch in Python, but I'm not using the Python code, I'm writing everything with a Go. And the reason to this is it's actually pretty easy to skip an understanding of some things and just copy paste some of the code or think that you understood something, but especially with NumPy, I think it's very easy to think, oh, I understand how certain things are working, because NumPy and the Python itself provides you like lots of the features when you deal with the metrics, computations, and so on. And in the previous video, well, 2 videos ago, I spent some time doing refactoring and fixing some of my mistakes. In the previous video, I finally continued doing some code, and right now we at chapter 9, I think, that is called backpropagation. And the goal of this chapter is basically we're implementing several backpropagation functions when we're trying to understand how we need to change weights after the model calculation, well, after the model training. And in the previous video, I spent some time diving into and implementing the categorical cross-entropy loss derivative code implementation, and we ended up with, with this function, which is, well, more or less optimized. And I actually thought yesterday after the video that I can skip even multiplications for the 0 values. I don't know what's happening. Sometimes right now, when I use tab, it doesn't insert the tab symbol, but rather it jumps to, I think, to one of the old placeholders. And one of the ways to fix it is to restart the NoVim. But for example, I need to do all of these calculations only when I have a 1 value. So yeah, just trying to take a look that nothing is, yes. So it's the same. And today I'm going to take a look at the softmax activation. Because I think, for example, if we take a look at where it's if we take a look at kind of one of the simple models that we created, for example, this one, we have the first layer, we have the activation relu function, which we already implemented the backward path. We implemented the backward path for categorical cross-entropy loss, and the only thing that's missing is the activation function. So here we are, but before this, we're going to dive into the math under this. And actually, I want to record a video on my main channel. So this is, well, I would say the main one is the talking one, and this is the coding one. And I want to record a video why, and kind of, there are people telling that, oh, you don't need, classic math for the software engineering. I mean, half of this book is actually implementation of some linear algebra. So for example, like in the previous 2 chapters, I've been recalling what is a derivative is, partial derivatives, and there are some rules how you calculate derivatives for the complex functions, and that's basically what we're implementing right now. So yeah, if you're interested, give me some heads up in the comments that you would like to see such type of the video. And actually, I'm trying not to do this too much, but if you can give me some heads up if you enjoyed this video or not, I would really appreciate it, because, well, I actually going to publish a video explaining what happens in my personal life and how it interferes with my work or this type of the videos. It's actually pretty hard to find the time and energy to record this type of the videos. So if you find them valuable, I would appreciate giving me some heads up. But okay, enough talking. So it's 7 minutes. Okay, let's go. Softmax activation derivative. The next calculation that we need to perform is the partial derivative of softmax function, which is a bit more complicated task than the derivative of the categorical cross-entropy loss. Let's remind ourselves of the equation of softmax activation function and define the derivative. So the softmax is we taking the value and we're taking an exponent and we turn it into the power of the value, and then we're doing the same for all of the values, taking the sum, and then we're taking this one value and dividing it by the sum, and that gives us the not the normal distribution but normalized distribution of the values between each other. And define the derivative. So where for this function we're looking for derivative from this value, that's and that gives us, this is the function, this is the parameter that we are looking for. When S denotes jth softmax output of its sample, so I denotes for the sample. This, for example, we have the, for example, in the spiral data or in the vertical data, we're returning 300 samples, and we're passing all of the samples through our network, and I denotes for this one of the samples that input array, which is a list of input vectors, output vectors from the previous layer, ig, j's softmax input for ith sample, L, big L, number of inputs, as we L number of inputs. So, well, basically, for example, in my case, that's, for example, 2, because I have 300 samples, and each sample consists from 2 values. So in my case, the softmax output should have the dimension of 300 by 2. Well, basically, by the way, let's test it that I'm not wrong. Right, so RC equals to loss value. Oh, that's not the loss value. Activation, second activation 2 out. What happens? Activation 2 output teams. Oh, okay. And here I have RNC, and if I go to the main function, I want to comment this, run this, and oh no, well, yeah, it returns the number of output classes, not the number of inputs. Okay. As we described in chapter 4, the softmax function equals the exponentiated input divided by the sum of all exponentiated inputs. In other words, we need to exponentiate all the values first, then divide each of them by the sum of all of them to perform the normalization. Each input to the softmax impacts each of the outputs, and we need to calculate the partial derivative of each output with respect to each input. From the programming side of things, if we calculate from the programmatical side of things, if we calculate the impact of one list on the other list, we will receive a matrix of values. Each input to the softmax impacts each of the output, and we need to calculate the partial derivative of each output with respect to each other, to each input. Each output with respect to each input. From the programming side of things, if we calculate the impact of one list on the other list, we will receive a matrix of. That's exactly what we'll calculate in here. We'll calculate the Jacobian matrix, which we'll explain later, of the vectors, which we will dive deep into soon. To calculate the derivative, we need to first define the derivative of the division operation. Okay. So for example, we have a function that is a division between two functions. Then the derivative of this function will be the derivative of the top function multiplied by the bottom function minus top function multiplied by the derivative of the bottom function and divided by result of the function square, well, of the bottom function square. In order to calculate the derivative of the division operation, we need to take the derivative of the numerator, multiplied by the denominator, subtract the numerator multiplied by the derivative of the denominator from it, and then divide the result by the squared denominator. I will be, honest, I'm not very good at using the English terms regarding the math. I think I told it in another video because I studied all of the things in a different language. And for example, one of the persons who have been watching my videos actually helped me to, for example, properly name how to say the derivative. So yeah, sometimes I might be saying very simple things, but yeah. We can now start solving the derivative. Okay, because here we have, so meaning that this is the, I guess this is the two functions thing, right? Let's apply the derivative of the division operation. Okay, so we have this function, this is the numerator, this is the denominator. So we have the derivative of the numerator, which is here, multiplied by the denominator, then we have the numerator multiplied by the derivative of the denominator and divided by the square value of the denominator. And at this step we have two partial derivatives presented in the equation. For the one on the right side of the numerator, right side of the subtractor, this one. Yeah, so this one, right? We need to calculate the derivative of the sum of the constant e, Euler's number raised to the power of z, where L denotes the consecutive indexes from 1 to the number of the softmax output L, with respect to z. The derivative of the sum operation is the sum of the derivatives and the derivative of the constant e raised to the power of n with respect to n equals e in power of n. Yeah, it is a special case when the derivative of the exponential function equals the exponential function itself, as its exponent is exactly what we're deriving with respect to those, its derivative equals to 1. Also know that the range 1 till L contains k. K is one of the indexes from this range exactly once, and then in this case the derivative is going to equal e to the power of that and zero otherwise. So we have this sum, and only in one place it will be the same value, all others with respect to different will be 0, so this is why we have the same value. The derivative on the left side of the subtraction operator in the denominator is slightly different case, because here we have ig and then we have ik. It doesn't contain the sum over all of the elements like the derivative we solved moments ago, so it can become either 0 if j doesn't equal k, or e to the power of this value if they are equal. That means starting from the step we need to calculate the derivative separately for both cases. Let's start with j equal k. In the case of j equal k, the derivative on the left side is going to equal e to the power of the z from indexes I and j, and the derivative on the right side solve the same value in both cases. Let's substitute them. The numerator contains the constant e to the power of that. I think this is here. In both the minuends, the value we subtract from, so here and here, so we can move it. Yes, this is what we're going to do. Then let's split the whole equation into two parts. We can also write the denominator as the multiplication of the value instead of using the power 2. We moved e from the numerator and the sum from the denominator to its own fraction, and the content of parentheses in the numerator and the other sum from the denominator as another fraction was joined by the multiplication operation. Now we can further split the right fraction, this one, into 2-1. So this divided by this and this divided by this, right? And that looks like 1, right? In this case, it's a subtraction operation. We separate both values from the numerator, divided them by the denominator, and apply the subtraction operation between the fractions. If we look closely, the left fraction turns into softmax functions equation. If we, the left fraction, this one, right, turns into softmax function equation as well as the right, this one. No. With the middle fraction solving to 1 as the numerator and the denominator are the same values. So in both cases I is for the sample, and j and k Note that the left softmax function carries the j parameter and the right one k, both came from the enumerators respectively. So full solution. Now we have to go back and solve the derivative in case of j doesn't equal to k. In this case, the left derivative of the equation solves to 0 as the whole expression is treated as a constant. So this is eliminated, so we ended up only with this one. The difference is that now the whole subtraction solves to 0, leaving us with the minuend in the numerator. Now, exactly like before, we can write the denominator as the multiplication of the values instead of using the power of 2. Well, yeah, then let's split this fraction. Well, this looks like the softmax and this looks like another softmax. So both fractions represent the softmax activation function. Note that the left softmax carries the j, the right one has k, but so kind of like the previous one. As the summary, the solution of the derivatives of the softmax function with respect to its inputs is. So if j equal k, we have the value of result of the softmax activation function multiplied, but they equal, right? Doesn't it mean that we can shorten it? It's not the end of the calculations that we can perform here. One left in this form will have two separate equations to the code and use in different cases, which isn't very convenient for the speed of the calculation. We can, however, further morph the result of the second case of derivative. Okay. Well, yes. In the first step, we move the second softmax along the minus sign into the brackets, so we can now add the 0 inside of them and right before the value. That doesn't change the solution, but now both solutions look very similar. They differ only in single value. Conveniently, there exists Kronecker delta function, which will explain soon. All the equation is one where we can apply it here, simplifying our equation further to Kronecker delta. Well, it's just another way to represent it. That's the final math solution to the derivative of the softmax function's output with respect to each of its inputs. To make it a little bit easier to implement in Python using NumPy, which won't be the case for me, let's transform, okay, basically multiply it softmax by both sides of the subtraction operation from the parentheses, okay. Okay, so we're going for implementation. We have this one, right? This let us code the solution using just two NumPy functions, which we'll explain now step by step. Let's make a simple example. So we have the softmax output and shape it as a list of samples. We are reshaping it into two-dimensional array, but what I have for the output, softmax, searching for the softmax, right? Softmax. Okay, in my case, that's two-dimensional array where number of rows represents number of samples and number of columns represents the output of the softmax activation function, which is the probabilities of the concrete category, right? So here we're reshaping it into two-dimensional array with one column. The left side of the equation is softmax output multiplied by left side of the equation. Yeah. The current curve delta equals 1 when both inputs are equal, 0 otherwise. If we will visualize this as an array, we'll have an array of zeros with ones on diagonal. You might remember that we already have implemented such a solution using np.i method. np.i returns I think two-dimensional array with ones on the diagonal and zero. So for example, for the every row we'll have a two-dimensional array like diagonal. Now we will do the multiplication of both of the values from the equation part. So we're multiplying the softmax output with those values. So basically we're taking one row and we're multiplying it for every row in this diagonal matrix. Okay, in that case I don't think that I need to reshape because I mean I can multiply it row by row, right? Why I need to reshape it? Well, they have done it in a way that this multiplied by this multiplied by this, and this on this, but it doesn't make much sense. You can do the same, but vertically. You can take this one, or maybe it's just a thing with NumPy, and multiply by this, you'll get the same. It turned out that we can gain some speed by replacing this by the final np-flat method call, which computes the same solution. Flat method creates an array using an input vector as the diagonal. Well, yeah, basically we need to, for example, we have a one row and we have a then two-dimensional array. We just need to, this one row that we have as an input, we should make it as, like a stairway. And that could be done by just, I'm taking an array, a vector as an input, and I'm returning a square matrix as an output, and I'm just going through all of the elements and using it, and I can set the diagonal something like, I don't know, I'll just write it well. And it returns two-dimensional array, right? I'm not sure if I'm going to use this particular params, but values, for example, I have len, which is the values, intent, func, diag, len. I'll make it the same. Then I'm making results, which is plot 64 and make length and for range results. What I'm doing, I'm creating an array. And 0 length and interesting. Can I make a slice with concrete values? Slice fill. No. Make. Okay, then let's write it in a simple way. If a j, right, if j equal I, then result equals to values. Okay, else results let's see, maybe I will write it using the GoNum if it will make easier, but right now that should be the case. How I can test it? I can, where's it? It's in the softmax. What can I do? I can create a testing array to make plot 64, for example, 3 and values okay. I think no. Plot 64. I think like this. 1. Okay, that's good. Then we take in the result, which is soft. No, I think it's a loss. Wait, where is it? Jack flag. It's an activation. Jack flag R and print res, right? Correct. So that's the result. So the first row, the second, and the third. Okay. Then the other part of the equation is multiplication of the two softmax output, the multiplication of the softmax outputs, iterating over A and K indexes respectively. Since for each sample the I index will have to multiply the values from the softmax functions output in all of the combinations, we can use the dot product operation. For this, we'll just have to transpose the second argument to get its row vector form. So we just multiplying the softmax output and the transposed one. Interesting. Okay. Here. Okay. I will hide it. So okay. Finally, we can perform the subtraction of both arrays. So we have the double flat of the softmax output. But here we're talking about one row, right? The result matrix of the equation and the array solution provided by the code is called the Jacobian matrix. In our case, the Jacobian matrix is an array of partial derivatives in all of the combinations of both input vectors. Remember, we're calculating the partial derivatives of every output of the softmax function with respect to each input separately. We do this because each input influences each output due to the normalization process, which takes the sum of all the exponentiated values. The result of this operation performed on the batch of samples is the list of the Jacobian matrices, which effectively form a 3D matrix. Okay, you can visualize it as column. Those levels are Jacobian matrices being the sample-wise gradient of the sample of the softmax function. This raises the question, if sample-wise gradients are the Jacobian matrix, how do we perform the chain rule with the gradient backpropagated from the loss function, since it's a vector for each sample? Also, what do we do with the fact that the previous layer, which is the dense layer, we'll expect the gradient to be a two-dimensional array. Currently we have a 3D array of partial derivatives. The derivative of the softmax function with respect to any of its input returns a vector partial derivatives, as the input influences all of the outputs. Those also influence the partial derivatives for each of them. We need to sum the values from these vectors so that each of these inputs for each of the samples will return a single partial derivative value instead. So instead of matrix, because each input influences all of the outputs, the returning vector of the partial derivatives has to be summed up for the final partial derivative with respect to this input. We can perform this operation on each of the Jacobian matrices directly, applying the chain rule at the same time, applying the gradient from the loss function. Using np dot, for example, of dot product, for each sample it will take the row from the Jacobian matrix and multiply it by the corresponding value from the loss function gradient. As a result, the dot product of each of these vectors and values will return a singular value forming a vector of partial derivatives sample-wise and a 2D array. So output, I think the output of the softmax activation function is two-dimensional array, right? Okay, so we have the single output, which is the first row, We calculate the Fabian matrix, which should be again a two-dimensional one, and then we, using the dot product, and that returns a vector, right? Calculate sample-wise gradient and add it to the array of sample gradients. So the d values is the same as the input. Well, the inputs is empty like. Okay, first we created an empty array, which will become the resulting gradient with the same shape as the gradient that we are receiving to apply the chain rule. The empty like method creates an empty and uninitialized array. Uninitialized means that we can expect it to contain this value, but we'll all set. In the next step, we're going to iterate sample-wise over the pairs of the outputs and gradients, calculating the partial derivatives as described earlier and calculating the final product. Jacobian matrix and gradient vector. Storing the resulting vector as a row in the input array. We're going to store each vector in each row while iterating forming the output array. Okay, so I will start the implementation, but I will continue tomorrow. But there are a couple of things. First, I need the inputs. Yes. Then, oh, not this. Then this one. Let's see. Okay, the first thing I need to define the inputs, and that will be the values, which is the dense. Then I need to initialize the inputs, and that will be the dense copy of the values. So it will create the. By the way, what we're going to, I mean, at which point? So we have. So the softmax activation function is the not the last one, right? So I guess the d values will be the results, the output. Well, not the output, it's the d inputs from categorical entropy loss, right? But we do enumerate. So for let's index equals to range of d values, but actually the d values and well, can I do this? Activation output dims equals to d values dims. No? Okay. It's too bad. Okay. I will assume, well, I should assume they're the same. Can I reach? All right. Index equals 0. Okay. Index is less than. I'm not sure if I need column. Okay, so we're creating the single output. Single output, and that should be d values at row view at index. And I think I need to transpose it because of the shape. It will give me, well, it should give me the column vector. Then we need to calculate the Jacobian matrix. Jacobian matrix equals to diag flat, and the diag flag is single output. Can I take the row? No, I cannot take the row. Okay, maybe row single. Okay. Okay, basically I will create first take row from d values, right? And then convert it into column vector of dense, then calculate diag let, then product between single output and single output t, and then product between Jacobian matrix and input d values. Oh, actually, no, take the row from activation outputs. Okay, this is the plan. I will continue, well, I will not continue actually tomorrow, I will continue the day after tomorrow because, no, I will continue tomorrow. Okay, thank you for watching, and I see you tomorrow. Bye bye.